Good evening. Welcome to today's class. Thank you very much for making time to join. Right, so today I wanted us to start on a new topic where we can look at modal logic, right? So we'll do a brief introduction and then we can get right into it. Right, so I think I've been seeing some few questions. I think after our class, I'll be able to have a 30-minute sit down with all the questions posted. Any questions, we can have a discussion in there. Then yeah, we should be good to go. All right, so modal logic. What about modal logic? We have talked of predicate logic, we have talked of propositional logic. We're now being introduced to a new form of logic, right? So where is it come from? What is it all about? So we worked in the binary, true and false, right? We worked in the predicates where we discussed models to say it is true under a specific model, can be false under a specific model, right? Now I want us to look at answering the question, how true is true? So that will be the main topic of discussion under modal logic, to say how true is true, right? So you'll find that something can be true to a point, right? Something can be true universally, something can be true only to a minority. So that level of truth or degree of confidence of the truth is what we're going to be discussing. We are focusing on things that are true, and we are looking at the extent of truthfulness and how it can be used, or how it can add value to our, to our data, to our logic, right? So we're going to start off with a little bit of modeling again, some models, right? But this time we're going to look at a completely different model, where we look at a model of modal logic, right? So it is going to have the normal. We are going to have in our world a set of elements called worlds, right? So it's a set of all the elements. That is our universal set, our domain where we are playing around, right? Then worlds are simply can be, or another way of saying worlds, states. It's a state, right? It's a state, and a state will have relations with other states. So relations of elements in the model, right? So a relation will exist between x1, x2, and x3, right? So x1 and x2, there's a relation there. If we have this, that is a relation. We can have a relation here, we can have a relation there, and so forth, right? So a relation R is called the accessibility relation. It links two worlds together. Then lastly, we have got what we call a labeling function. It is responsible for assigning elements or intrinsic properties of a world, right? So the relational accessibility relation tells us how the world interact with other worlds, right? The labeling function tells us what is contained within the particular world, right? Now, if we have a model which has got worlds, relations, and the labeling function, right? If we have got such a model and we have got X, let's say X is a world in this, is an element of the world, it's a world basically, right? We'll define a formula phi to be true in world X, right? This is done using satisfaction. Remember satisfaction, when we started with propositional, we talked of how satisfaction is more or less the standard or the most common way of modeling. You want to satisfy a particular scenario, right? So satisfying a particular scenario does not mean you satisfy all scenarios. You are just using something that is fit for purpose for that particular problem, right? Now, every world is going to satisfy a tautology. Either it will contain P or not P. Every world is not going to satisfy a contradiction. There's no way not P can be there and P can be there. Right. Then we say A world will satisfy a formula P, right, if and only if P is an element of the labeling function of that world. So if we've got world X, right, we say X satisfies P if and only if P is an element of that world. Right. Then we can have a world satisfies the negation of something if and only if the world does not satisfy phi. It will satisfy the negation of phi if and only if it does not satisfy phi. And then if we have a formula, if this is a formula and this is a formula, then a world will satisfy a particular formula, the conjunction of two formulas, if and only if it satisfies them individually. You have to satisfy it individually, and here satisfy it individually as well. Then a disjunction, for you to satisfy a disjunction, you need to satisfy either this or that, one of them. One of the two need to be satisfied. Then implication is always a little bit tricky, right? When you satisfy an implication, it means you are looking for an instance, or each time you satisfy the left-hand side, you have to satisfy the right-hand side, right? The other way of satisfying this is if you cannot satisfy the left-hand side, then by default you satisfy the formula, because false implying anything true or false becomes true. Right. So we say you satisfy an implication if and only if X will satisfy the right-hand side whenever it satisfies the left-hand side. Right. Then biconditional, you satisfy biconditional if and only if it will satisfy the left-hand side, if and only if it will also satisfy the right-hand side. Right. That is how it works. So these relate to labeling functions. Right. Now, we want to look at new operators that are now being introduced. We have a box and we have a diamond. Right. What does box mean? What does diamond mean? So these one now speak to the relational matrix that we have. R, our relational matrix. Right. Now, we have box, right, and diamond. Box, when we say box phi, we're saying, or let's say x1 satisfies box phi. We're saying all the world that x1 goes to, that x1 will go to satisfy the formula phi. Like that. All the worlds that x1 goes to or will go to will satisfy phi. Meaning to say, if you have got x1 and you have got x2, x2, say, and x3, right? If x1 goes to x2 and x1 goes to x3, right? x1 will satisfy box phi if and only if x2 satisfies phi and x3 satisfies phi. Like that. Any questions there? Okay. Now, we can also look at diamond, right? Or maybe before you go to diamond, right? The definition says all the worlds that x1 goes to will satisfy phi, right? So if we were to say, for example, maybe let me write this in red, x2 satisfies box phi, would that perhaps be true or false? x2 is not going anywhere. So would that make the statement true or false? Right. So now this statement is very tricky because it's not going anywhere. But what is the definition of box? The definition says all the worlds it goes to contain phi, right, or satisfy the formula. Now, in this particular case, there is absence of evidence. What do I mean? We do not have a counterexample to say, here is a world that x2 goes to, but it does not satisfy phi. So this one will remain true. And we say that it is vacuously true. Vacuously true. Because there is no counterexample to use to say, oh, x2 goes to x5, but x5 does not satisfy phi. Now we can go to diamond. So when we're looking at diamond, we're saying if x1 satisfies diamond phi, what does this mean? It means to say there exists a world that x1 goes to. X1 goes to that satisfies phi. So in this particular case, where we have x1, x2, x3, right, we're saying x1 is going to satisfy diamond F, diamond phi, if and only if x2 satisfies phi or x1 satisfies phi. Either one of the two. Right. If we had more, x1 was going to x3 and stuff, it was just going to be all more of those. But that is how diamond works. In the event of having, for example, x2, does it satisfy diamond phi? Right. From the definition, it tells us that there exists. So to prove this, I have to give you a world it goes to that will contain or that will satisfy a particular formula. In this case, x2 satisfies diamond Q is not going to work out because I cannot give a world that it is going to that satisfies the given formula. That is how it's going to be. So this is going to be false. And why? Because there does not exist. There does not exist a world. A world that satisfies phi. Satisfies phi. Okay. Any questions? Model for modal logic. Right. Now, we can start looking at some questions, right? I'm gonna throw you a little bit in the deep end to start with, but maybe let's start with something as simple as this. Yeah, this is simple enough. Right, x3, does x3 satisfy this particular guy here? Right. For you to satisfy a conjunction, what needs to happen? You need to satisfy the left-hand side individually and the right-hand side individually. So we'll say x3 satisfies diamond P and diamond Q if and only if x3 satisfies diamond P and x3 will also satisfy diamond Q. And this will happen. When does this happen? For x3 to satisfy diamond P, it means x3 has to go to some world that satisfies that. So if and only if x3, x1, if x1 is going to satisfy P. We see it does satisfy P, therefore this part is true. You now need to prove this part. X3 satisfies diamond Q, right? So it's going also to if and only if X1 satisfies Q. So it also satisfies Q. So therefore, this whole formula becomes true. Right. Now, how do you respond to this? How do you write it in the exam? So it satisfies that since X3 satisfies P and X3 satisfies diamond Q. X3 satisfies diamond P since X1 satisfies P and X3 satisfies diamond Q since X1 satisfies Q, like that. Right. What do you think of this one? Do you think it satisfies or it does not satisfy? Your thoughts? Do you think this formula satisfies the model or the world X2 or not? Yes, no, maybe? Right. It's an implication. If you have to satisfy this, you are saying every time you satisfy this, you have to satisfy that. Right. So question number 1, does X2 satisfy box not P? Right. So X2 is this one. Does it satisfy box not P? All the words that it goes to, where does it go? It goes to X1, it goes to X3. Right. So it goes to X1 and it goes to X3. Do they satisfy not P? Right. Do they satisfy not P? X1 does not satisfy not P and X2 satisfies not P. Right. So since this is false, then this is going to become false. Right. This is going to become false. And false implying anything becomes true. Right. So false implying anything becomes true. So how do you respond to this? You're saying X2 will satisfy box not Q, implying box not P, right? Since X2 does not satisfy box not P, then the implication becomes true, right? And we know all worlds X can satisfy true holds, satisfies the truth. If a statement is true, then a world will satisfy it. All right. Yes, Anastasia?
I just want to find out where you wrote X2 satisfies box not P implies box not P. Shouldn't that be a not Q?
It's not Q, correct.
Okay.
Thank you. All right. Next one. Box, diamond. What is happening here? Right, so let's familiarize ourselves with our brackets. So we've got this, because our operators box and diamond are unary predicates, they take one input. We're also going to have another bracket here, like that. So x1 satisfies box, and this is formula. So x1 satisfies box phi. What is phi? Phi is going to be box, diamond, P and Q. Right. So if we were to redo this, we'd say this will satisfy that if and only if x1 goes to x2, if and only if x2 satisfies diamond, box, diamond, P and Q. And this will only happen if and only if x1 satisfies diamond, P and Q, and x3 satisfies diamond, P and Q. Right. So it's an AND. Now, does x1 satisfy that? And this will only happen. So x1 satisfies diamond, P and Q if and only if x2 satisfies P and Q. Right. We see already that x2 does not satisfy P and Q, therefore x1 does not satisfy that, right? And this does not satisfy that, this does not satisfy that, therefore this does not satisfy that. Right. You see what's going on there? Yes. It is a nested function. So put your brackets in, right? Put your brackets, and start with the biggest one, then move in, then P and Q. Okay. Questions, guys? Now we can have.
Sorry. Sorry about the background noise. I'm still on the road. I don't know if maybe when we're explaining, can you explain showing the errors? I'm very lost. I'm trying to catch up, but you see also when you put those brackets, I'm very lost with those pieces.
All right. So we have a string of operators, right? And we have P and Q. Right. We know these are unary functions or unary operators. These are unary operators. They take in one input. So the input to this one is going to be this. Right? So we can group this together like this. The input to this one is going to be this whole bracket here. So we can group it like this. So our main function is a box, right? That says all the words that in this particular case x1 goes to. You have to satisfy this formula. Right? So this phi is in this particular instance is speaking to all this. Right? So you are now grouping and saying, okay, box satisfy that. Then when you get there, you are now saying does x2 satisfy phi? What is phi? Phi is equals to box, diamond, P and Q. So it's another case of box that. Does it satisfy this? Then, okay, well, what does x2 goes to? It goes to x3 and it goes to x1. Does x1 satisfy? Does x1 satisfy? Now we're looking at this, right? And x3, does it satisfy that? Right. What is this? This is going to be diamond P and Q. This will be diamond P and Q. And then you continue breaking it down like that, where you get to saying, okay, right, this is something that we are familiar with now. You can tell whether or not there exists a world it goes to that will satisfy that particular formula. Right. In terms of, I don't know if that makes any sense or that clears your question. Second half of the question.
Oh, that means when we are in X1, you need to check that diamond P and Q, and then we go to X1 and check it for the Q and the P.
Yes. So to check X1 satisfies diamond P and the Q, this will only happen if and only if, right? What does X1 go to? X1 goes to X3. So X3 is to satisfy P and Q. That is, it has to contain P and Q. Make sense? No, yes?
Okay. Can you go back? I just want to see if it's containing that P and Q.
Yeah. So X2 is not P. It does not satisfy P and Q.
Okay, I see. Yeah, I keep on referring. That means you know to keep on referring to the diagram always and check with the inside the box.
So if it's too complicated, break it down and simplify it to what your theorems say, what you are familiar with. Let's look at more examples. Right, box, not P and Q, X3. So X3 will satisfy this if and only if it's, so we're going to put our brackets here again, box, whatever this is. So X1 needs to satisfy box, not P and Q. So why? Because X3 goes to X1. X1 needs to satisfy not P and Q. To satisfy not P and Q, right, it means that it only happens if and only if, because X1 only goes to X2. X2 satisfies not P and Q. X2 satisfies not P, but it does not satisfy Q. Therefore, X2 does not satisfy not P and Q. Therefore, X1 does not satisfy that, and this does not satisfy that.
Or the box in front of those curly brackets, it means that you need to go outside of that box.
Sorry?
To go to the next one. The box in front of those brackets, it means that you need to check the circle next to
This one.
The box is actually all the boxes that are in front. It means that you need to check the next circle.
Yes, we need to check where it goes, because box says whatever it is related to is the one that needs to satisfy the formula.
And then if there's two arrows out, that means those two boxes or circle need to satisfy the same thing inside the box.
Both the worlds or all the worlds that it is going to need to satisfy this formula. In this particular case,
Okay,
it's lucky just that it's one.
Yeah, it's only one.
Mm-hmm.
Okay.
Right. Okay. Then diamond P and diamond Q, you should be able to have an idea of whether it satisfies or not. Does X1 satisfy the given model? Does X1 satisfy the given model? Anyone? Right. If it satisfies this, then it has to satisfy that as well.
It doesn't satisfy P, but it satisfies the other side.
Right. So let's check. Does X1 satisfy negation of or diamond P? So the question is there a world that X1 goes to that contains Q? So X1 satisfies Q. It satisfies this since X3 satisfies P, right? So since it satisfies P, it means that this is true. Now this has to be true. This has to be true, right? So does X1 satisfy P, right? It satisfies P, X1 satisfies diamond Q, sorry, since X3 satisfies Q. So what do we know? We know that X5 satisfies diamond P, implying diamond Q, since X1 satisfies diamond Q whenever it satisfies whenever, let me write the proper notation, whenever X1 satisfies diamond P, like that. That's an implication. So I think, was it Homozo? Yeah. So we're saying, does it satisfy this? If yes, then does it satisfy that?
Sorry, can you repeat again? That means the first P, that one we check on X3, and then the Q we check on X2. Am I correct?
Not really. So the 3, we're saying we can check on 2 and on 3. We can also check on number 3. It's fine. It's not, you are not, because we checked on number 3. So they just need to be existent. I need to have a world it goes to that will satisfy it. So 2 does satisfy Q and 3 does satisfy Q. But we just need one of them to prove our case.
Or that means a diamond, it doesn't need both arrows to be correct. It has to need one.
At least one, yes.
And then tell me about the next diamond, the Q. That one we sourcing from X1 or from X3.
So X1, right? X1 satisfies diamond Q. So we're saying, is there a world that X1 goes to that contains Q? So we go, does it contain Q? Yes. Does it contain Q? Yes.
Oh, I see now. See that the big difference is that the previous one, it got some boxes in front. That's why we keep on popping to a box. This one, it only have one box in front of each and every letter. I see.
So box O, diamond, at least one.
Got it.
So this one is a disjunction. You would need to satisfy left-hand side or right-hand side. Right. X2, does X2 satisfy, I'm going to check the smallest one first. Does X2 satisfy box Q? So all the words it goes to, X2, it goes to X1. So does X1 satisfy Q? Yes, it does. Does X3 satisfy Q? Yes, it does. So X2 satisfies that since X2 satisfies that because X1 satisfies Q and X3 satisfies Q. Like that. Okay. Let's look at this one. So here we have to prove a conjunction, satisfy a conjunction. So it has to satisfy the left-hand side and the right-hand side. Let's start with the smaller one. Does X3 satisfy diamond P? Where X3, is there a world that X3 goes to that satisfies diamond P? Yes, they exist. So it satisfies this since X1 satisfies P. Right. Then does X3 satisfy box P and Q? So in all worlds it goes to need to satisfy P and Q. So X3 goes to only one world, which is X1. So it satisfies that since X1 contains P and it contains Q. So this is going to be true. Questions there? Is the lights coming on? No, yes?
Yeah, I'm with you. Now I see this.
Okay. So let's move on to sort of a sister concept of what we're doing. Right. I think, okay, this is the last one. Box not P. So we're saying box not P. X3. Does X3 satisfy this? It will satisfy this if and only if all worlds it goes to X1. X1 satisfies diamond P. And this will be true if it goes to X1 and X3. X1 satisfies P or X3 satisfies P. But X3 satisfies P, therefore X1 satisfies diamond P, therefore X3 satisfies box diamond P. All right. Now we say a formula is valid if and only if it is true for all models. Right, it is true for all models. So a formula like P or not P, it is true for all models. Right. That is a formula. Right. Now, a formula, if it is not valid, if a formula is not valid, right, it just means it does not satisfy all the models. It can satisfy one or two, but not all the models. There exists a model it does not satisfy. Right. So rarely do we get valid formulas. Right. We have formulas that can satisfy a particular word, remember, like we're doing with predicate logic, but are not necessarily valid. So and when we say a formula is true for a model, we say a formula is true for a model. A formula is true for a model if and only if it is true for all the worlds. if it, and only if it is true for all the worlds. So if you have a formula and you want to say it is true for a particular model, then it has to be true for all the worlds. So this particular question is now asking to say, find a Kripke model that does not satisfy the model logic formula before. So it doesn't have to satisfy diamond P implies, so box P implies box P. Right. Now they say use, you have got three worlds. You've got three worlds to work with. And also explain why it does not satisfy the formula. Right. So box P, if it does not satisfy, it means this has to be true and this has to be false for at least one of the worlds. So box P says we've got x1 here, x2, and x3. Whenever you satisfy this, you have to satisfy that. So box P says if does x1 satisfy box P? We want x1 to satisfy box P. So if x1 goes to x2, then x2 needs to satisfy box P. Then if x2 goes to x3, then x3 needs to satisfy P. So you can put P in here. So in this particular case, x1 satisfies box P. Now, how do we make it not satisfy box P? So for x1 to satisfy box P, then x2 needs to contain P, sorry. But if I put something like Q here and I don't put P, then it means x2 does not satisfy P, therefore it does not satisfy box P. So now x1 satisfies the left-hand side but does not satisfy the right-hand side. So this formula is not true for x1 in this model. Whatever else we then put, we find that this, we can put other arrows and stuff like that. But x1 will not satisfy this particular model. Or will not satisfy this particular formula. Now, there are a million possible answers that you can possibly put here, right? So it's just asking you to apply your knowledge so far to generate a world that does not, a world that does not take in the, a model that does not accept this formula. Right. Let's look at another one. Want a Kripke model that does not satisfy the model. So it's box, a diamond, it's diamond, P. If you don't want to satisfy diamond, P, and you've got three worlds, you can just have something like this. PQ. You can just have something like this. What will this do? There does not exist. So this will fail because there does not exist. We looked about it. If a world does, particular world does not go anywhere, then there does not exist. Right. So yeah, you can put like whatever, but one of them needs not to leave and have anything to leave. Right. Questions?
Oh, you said on this one, the answer you just put circles and then you don't put any arrow. That's the answer.
That will work as well. So there are a million possible answers. You can generate a million possible answers here, literally. You just need to come, like we're coming up with models, you have to do the same here. Right. Right. So now they're saying that give a formula that has got at least one model logic connective that does not satisfy the given model. Right. So to do that, we need to come up with a formula. So you have to use at least box or diamond, right? So again, there are a million possible answers. Right? And you have to be looking at your model, right? So it has to be false for at least one world. So we can say if you do not contain P, let's say all the worlds you go to should not contain P as well. Let's look at this formula, right? If we look at X or A contains P, so it makes this false. So A, false implying anything will become true. So A fulfills it. B contains P, so false implying anything will become true as well. Right. C is here. Right. C contains nothing. It satisfies not P. Then does it go to a world that doesn't satisfy? All worlds it goes to should not contain a P. So we have true, and then it goes to B, which satisfies P, therefore it is false. So this is our counterexample, why our formula will not satisfy the given model. Even D as well, D does not satisfy P, and also it goes to a world that does not satisfy P, that makes it true. So it's true and true here. So mine is not the most correct one. Mine is not the only correct one. Mine is just one of those that will make it true, because C makes it correct. And any questions? So this is question 3.1 and 3.2 in the exam, and it takes up plus or minus 13 to 15 marks. It's not so difficult. You see, once you start doing one or two questions, you start coming right. All right.
Do they ask the second one? The first one seems to be easy. The second part, I think, I need more practice. They come both.
Yeah, true. But I also feel that it's just a matter of doing 3 of those, and then the 4th and 5th one, at some point you start, okay. It will start ringing now to say, you know what, the little things to look for and stuff like that. So I just want you guys to look at those type of questions, just practice them. Right. So I'll see you guys again tomorrow. We'll complete off chapter 3, and then from Tuesday we can start doing practice questions. So from Tuesday, I want you guys to take lead, bring all the questions that you have, and then we can tackle them. Right.
Oh, so, tell me, are we done with all the? I think we're done with all the chapters.
With all the
chapters, for example.
No, we'll finish chapter 3 tomorrow, and then we'll be done.
All right.
Okay, fantastic. Okay, enjoy the rest of your weekend, and I'll see you guys fresh next.
Did Edmund get back to you in regards to when the other videos are going to be uploaded?
The videos, how many have been uploaded so far?
I think chapter 2 has been uploaded. Chapter 3 hasn't, but none of the revision classes have been uploaded.
Okay, they're supposed to be done by this afternoon. I'll just follow up again, and then I'll update you on the group just now.
Okay, thank you.
Cheers, bye.